Hello, my awesome chemists. We are working on chapter 12, Stoichiometry, and we are going to start worksheet 2. And in worksheet 2, we're going to review what you did in worksheet 1 and then also talk about percent yield. So let's look at number 1 here, which is review from worksheet 1. It says, what mass of sodium chloride is produced when chlorine reacts with 0.29 grams of sodium iodide? So since it's talking about a chemical reaction, we probably want to write the chemical equation for what's happening. So what mass of sodium chloride? So I know sodium chloride is ionic. Sodium is Na+, chloride is Cl-, and so it's NaCl. And it says it's produced, so it comes after the arrow. When chlorine reacts with 0.29 grams of sodium iodide. So chlorine is reacting with sodium iodide. Chlorine is Cl2 because it's diatomic. Sodium iodide is Na+, I-, so it's NaI. Now you try to balance this and it doesn't really make sense because you have iodine on one side and not on the other side. Well, that's because there's another product they didn't tell us about, but that's not a problem. You guys are expert chemists. We've already gone through chapter 11. You know that this is a single replacement reaction because you have an element with a compound. And remember, with single replacement reactions, you look at the element, you say it's a nonmetal compared to the other nonmetal, which is iodine. You say chlorine is more reactive than iodine. It's not in a compound, so a chemical reaction will occur. The chlorine will kick out the iodine, so now you have iodine by itself as one of your products. Iodine is diatomic, so I2. And then your other product is NaCl. So then you're going to balance it. So you need 2 NaIs and 2 NaCls. After you balance your equation, I recommend that you write down what you have and what you're looking for. So I'm given 0.29 grams of sodium iodine, and I'm asked what mass of sodium chloride I would produce. So I'm given grams of one substance. I'm looking for grams of another substance. Remember, the only way to link between different substances is through moles and the molar ratio. So let's review our mole chart from right here. And we talked about this last time, but let's review it real quick. So if you have moles of a substance, you can go from moles to particles using Avogadro's number. That 1 mole is 6.022 times 10^23 particles. You can also go from moles to grams using the molar mass, so 1 mole and then the number of grams from the periodic table. You can also go from moles to volume, or liters, if it's a gas at STP by saying 1 mole is 22.4 liters. You can do the same thing with substance B. So you can go to particles of B, volume of B, or mass of B. But to link between two different substances, substance A and substance B, you need the molar ratio. And the molar ratio you get from the coefficients in the balanced chemical equation. So you can go from moles to moles. So you can also, if you look at this chart, go from particles of A to particles of B using the molar ratio as well. So you'd still use the ratio from the equation, but you'd use that number next to the particles of A and next to the particles of B. So you can go directly or you can go the long way. Why can you go directly? Well, the reason is because this step is going to cancel with this step, because one time you're going to multiply by Avogadro's number and the other time you're going to divide by Avogadro's number. And so those two steps cancel, so you can just basically do this step from particles to particles. Same thing with volume if it's a gas at STP. So if you're given volume of one of them and you're looking for volume of the other one, you can go the long way, the 3-step way, or you can go directly, again, using the molar ratio, which you get from your equation. And the reason you can go directly is because this step will cancel with this step, because one time you're multiplying by 22.4 liters, the other time you're dividing by the 22.4 liters. And so this step with this step cancel, and you only have this step that is left. And so you can use the molar ratio from the equation using liters and liters. But if you take a look at mass and mass, there is no shortcut. So if you're given mass of one of them and you're going to the mass of the other one, you can't go directly. The reason is because this step does not cancel out with this step. Why not? Because the molar mass of A is going to be different from the molar mass of B. So if you're given mass of one of them and you're going to mass of the other one, there's no way to do a shortcut. You have to do the three-step problem. So this question is a three-step problem. It's a mass to mass. We are given mass of one substance. We are given the mass of the NaI, and we are looking for mass of the other substance, which is the mass of the NaCl. And so we have to go through moles. So we're going to go from grams of NaI to moles of NaI using the molar mass of NaI. Then we're going to go from moles of NaI to moles of NaCl using the molar ratio from the equation. And then we're going to go from moles of the NaCl to the grams of the NaCl using the molar mass of NaCl. So let's do that. So back to our worksheet here. So we're going to write down what we have. So 0.29 grams of NaI. We're going to start a conversion factor. We're going to put grams of NaI on the bottom so they cancel. And remember to link between any two substances you need to get to moles. So we're going to go to moles of NaI first. And to go from grams of NaI to moles of NaI, you use your molar mass. So you put 1 next to your moles. And for the molar mass, you add up a sodium and an iodine. Their masses from the periodic table. And together they end up as 149.9 grams. Grams cancel, and you're now at moles of NaI. So now you go to moles of the substance you want. So we're going to go from moles of NaI on the bottom to cancel to moles of NaCl. And to do that, you use your molar ratio, which is in the equation here. So 2 and 2. And moles of NaI cancel. You're now at moles of NaCl. So the last step is to go from moles of NaCl, which goes on the bottom, to cancel, to the grams of the NaCl. And you do that using the molar mass. 1 goes with the moles, and next to the grams you add up a sodium and a chlorine. That ends up being 58.5 grams per mole. Your moles of NaCl cancel, and you end up with grams of NaCl. So in your calculator, you're going to do 0.29 times 2 times 58.5 divided by 149.9 divided by 2. All that together with 2 sig figs gives you 0.11 grams of NaCl, and that's your final answer. So in general, with stoic problems, what you want to do is find the moles of the substance you have information about, which in this case is the NaI. So this step was to find moles of the substance you have information about. Then you go to moles of the substance you're interested in, so that's this step. And then finally you answer the question, whatever it is, if it's grams or volume or whatever, which is this step right here. Okay, so let's look at number 2 now, and we're going to look at percent yield. So it says, when calcium carbonate is heated, it decomposes into calcium oxide and carbon dioxide. What is the percent yield if this reaction, if 24.8 grams of calcium carbonate is heated to give 13.1 grams of calcium oxide? Lots of stuff going on here. First thing I should think of, it's talking about a chemical reaction, so I should probably write out the chemical equation for it. So let's do that. So it says, when calcium carbonate is heated, it decomposes into calcium oxide and carbon dioxide. So it looks like calcium carbonate is my reactant. And so it's ionic. Calcium ion is Ca2 plus, carbonate is CO3 2 minus. So calcium carbonate is CaCO3. So when it's heated, it decomposes. So arrow, it's a decomposition reaction, to produce calcium oxide. So calcium 2 plus, oxide is 2 minus, so CaO, and carbon dioxide, which is CO2. Let's balance it. 1 calcium, 1 carbon, 3 oxygen. So This one's no fun. It's already balanced for us. I'm going to go ahead and write down what I have. I have 24.8 grams of calcium carbonate. And I have 13.1 grams of calcium oxide. And I'm asked for percent yield. What is percent yield? So let's write down what percent yield is first. Percent yield the equation for it is the observed mass of product over the theoretical mass of product and then times 100%. So what does that mean? Percent yield tells us how well our experiment went. So when I'm doing these calculations like I did in number 2, where I said, oh, well, if I start with 0.29 grams of NaI, I'm going to form 0.11 grams of NaCl. That is theoretical mass. So in theory, if everything goes well, if we live in a perfect world, it's a utopia, no sources of error whatsoever, and I use up all my 0.29 grams of NaI, I should end up with 0.11 grams of NaCl. So this is a theoretical calculated value. If everything went great, all reactions went to completion, no sources of error whatsoever. The real world, though, not all reactions go to completion. We do have sources of error. Maybe our product is wet, or maybe we lost some in transfer, or some kind of source of error happened. And so in reality, the mass that we end up with of the product is not always the same as what we calculated that it should be. And so the observed mass is the value that we actually get when we carry out our experiment. It's observed in the lab. Versus the theoretical mass is a calculated value similar to this right here. This is a calculated value. If, again, we lived in a utopia and everything was perfect, this is the mass of the product that we should get. So we compare what we really get as the observed versus what we should have gotten theoretically and multiply by 100%. And that tells us how well the experiment went. The closer, obviously, this number to 100%, that tells us the better our experiment went and the less sources of error happened. The farther it is from 100%, obviously, that means, different sources of error happened. So let's read this again. It's telling us we have 24.8 grams of calcium carbonate. And when we carried out our experiment, we ended up with 13.1 grams of calcium oxide. What is the percent yield for this reaction? So we are looking for percent yield. So the first thing you want to say is percent yield is equal to observed mass over theoretical mass and then times 100%. Now it's important to know mass of what. So this is the most common mistake when it comes to percent yield problems on the test, is that people plug in the wrong substance. So percent yield, what is yielded, what you end up with. So that should be a product. It's always mass of product. How much product did you get versus how much you should have gotten, right? And so I see a lot of people putting in mass of reactants or, different things. And so be careful that it's mass of product. Now we have two products here. One of them we have information about. The other one we don't have any information about. If you're given information about all your products, then it should be the total of all your products. So if we had information about calcium oxide and CO2, we should put both of them in here. But in this case, we're only given information about the calcium oxide. So in this case, we're just going to calculate the percent yield for just the calcium oxide. Okay, so it's important to know which substance you're doing this for. Okay, great. So do we have the observed mass or the theoretical mass? Well, we have one mass. We have that 13.1. So which one is it? Is that observed or is that theoretical? Well, this one's the observed mass. The reason I know that is because it's telling us that this reaction happened and we ended up with 13.1 grams. But also, observed mass you cannot calculate. Like, it's going to be given to you. Theoretical mass is usually calculated. So usually, I'm going to go ahead and write that down here before I change my color. So usually this number is calculated. And this number is usually given unless you are actually doing a chemical, like a lab and getting the data to get that number. So observed is always given either in the question or in the lab. The theoretical is a number that you calculate. So we have our observed value, but we don't know what the calculated or theoretical value is. So that's what we're trying to find. We are trying to find the theoretical mass of the calcium oxide. That's what we're trying to find so that we can plug it in here to find the percent yield. So how do we find the mass of the CaO? Well, you start with your reactant and you say, if I use up all of my reactant, how much of this product should I theoretically get? So this step is very similar to pretty much the same thing as this right here, where I'm given grams of the reactant and I'm solving for grams of the product. So remember, this is a three-step problem. Let's look back here. You're given grams of your reactant and you're trying to find grams of your product. This time, my reactant is the calcium carbonate and my product is the calcium oxide. So it's a three-step problem. First, I'm going to go from mass of calcium carbonate to moles of calcium carbonate, then to moles of the calcium oxide, and then to grams of the calcium oxide. So let's do that together. So I'm going to write down the grams of my reactant. And I'm going to first go to moles of that. So grams of calcium carbonate on the bottom, moles of calcium carbonate on top. To go from grams to moles, you use your molar mass. So 1 goes with the moles, and then you add up a calcium, a carbon, and 3 oxygens. This ends up being 100.1 grams. Grams cancel. Next, you put moles on the bottom. And you're going to go to moles of what you're looking for, which is the calcium oxide. You get this from the molar ratio, so 1 to 1. And so now your moles of calcium carbonate cancel and you're at moles of calcium oxide. Now you're going to go from moles of calcium oxide to the grams of the calcium oxide and use the molar mass for that. So put 1 next to the moles, and then for the mass you add up an oxygen plus a calcium. This ends up being 56.1 grams. And moles cancel. And so I do 24.8 divided by 100.1 times 56.1. Anything on top you multiply, anything on the bottom you divide. And you end up with 13.9 grams of calcium oxide. This is your theoretical yield or theoretical mass. So theoretically, if we lived in a perfect world, there were no sources of error whatsoever, I should have gotten 13.9 grams of calcium oxide. When I actually carried out my reaction, I only got 13.1 grams. So what is my percent yield? So you take your observed, which is 13.1, and you divide that by what you theoretically should have gotten, which is 13.9 grams times 100%. And this ends up being 94.2%. And that is my answer. Each reaction has a different percent yield, obviously, every time you do it. But some reactions go pretty close to completion. So, you know, a percent yield in the 90s would be reasonable. Some reactions barely go to completion. And so for some reactions, a 20% yield is fine. Also, remember that, you know, it has to do with whether the reaction goes to completion, but also sources of error. So my question to you is, we just saw that we can have a percent yield that is lower than 100%. Can I have a percent yield that is higher than 100%? The answer is yes. So some of you might say, well, I can't create mass, right? I can't get over what I should have. Well, you can't destroy mass either. You can't get below what you should have gotten, right? But sources of error happen. So just like you can lose some product in transfer and get lower than 100%, maybe your product is wet or has some sort of impurity. So when you mass it, it seems like it has a higher mass than it should. And so then your percent yield would be higher than 100%. So you can equally get a percent yield that is higher or lower than 100%. All right, I'd like you to finish worksheet 2 to practice. Remember that the answers are at the end of the worksheet, so you can check your work and let me know if you have any questions as always. Bye, guys.